Tonight, the moon may seem like humanity's next great home. It hangs peacefully above Earth, glowing in the darkness, waiting to be explored. But beneath that quiet surface lies a world far more dangerous than most people realize. Many assume Mars is the harshest place humans could ever live. The reality is far more surprising. The moon exposes settlers to extreme temperatures, relentless radiation, deadly lunar dust, and dangers that could threaten every moment of survival. Before drifting off into tonight's journey across the solar system, take a moment to like the video and subscribe to Cosmic Bedtime Stories. Now settle in, relax, and discover why living on the moon could be far more dangerous than Mars, and why the truth is worse than most people think. Human activity beyond Earth begins in an environment where natural conditions do not support life in any familiar form. The comparison between the moon and Mars starts at a broad level, where both bodies exist inside the same solar system, yet present sharply different physical realities. The moon represents a near-airless rocky surface directly exposed to space. Mars represents a distant planet with a thin atmosphere that still interacts with sunlight, dust, and seasonal cycles. These differences shape every aspect of survival, from radiation exposure to temperature stability and the behavior of surface materials. On the moon, the absence of a meaningful atmosphere means there is no air pressure in the conventional sense. Any exposed liquid water would not remain stable, and gases escape immediately into space. The surface exists in direct contact with the vacuum environment of space, a condition where particle density is extremely low and collisions between particles are rare. This leads to a setting where heat transfer occurs mostly through radiation rather than conduction or convection. As a result, temperature control becomes extremely difficult for any structure or biological system attempting to operate there. The lack of atmospheric buffering also means that sunlight strikes the surface with full intensity during lunar day, while darkness brings rapid cooling when the surface rotates away from the sun. Mars, by contrast, retains a very thin atmosphere composed primarily of carbon dioxide. Although the pressure is still far below Earth's, it is enough to create measurable weather phenomena and allow limited heat transfer through atmospheric motion. This thin air does not support human breathing and does not provide significant protection from space radiation, but it does introduce a layer of environmental interaction that the moon lacks entirely. Dust can be lifted and carried by winds, and seasonal changes influence the distribution of atmospheric gases, especially carbon dioxide that freezes and sublimates at the poles. From a structural perspective, both environments require sealed habitats for human survival, yet the challenges differ in nature. On the moon, engineering focuses on resisting vacuum conditions, extreme temperature shifts, and micrometeorite impacts that are not slowed by an atmosphere. On Mars, engineering must also account for atmospheric dust infiltration pressure differences and long-term exposure to chemically active soil known as regolith. Each environment introduces stress factors that accumulate over time, affecting materials, electronics, and biological systems differently. Radiation exposure is a shared concern, but its interaction with each environment is not identical. Without a protective magnetic field and thick atmosphere like Earth's, both the Moon and Mars are exposed to solar energetic particles and galactic cosmic rays. However, the Moon experiences a more direct and unmoderated flux because there is no atmospheric column to scatter or reduce incoming particles. Mars provides partial shielding through its thin atmosphere, which can slightly reduce the intensity of lower energy radiation at the surface. This difference, while not sufficient to eliminate risk, creates distinct long-term exposure profiles for potential inhabitants. Thermal behavior also highlights the contrast between these two worlds. The Moon experiences long periods of daylight and darkness due to its slow rotation, relative to its orbital cycle around Earth. These cycles lead to extreme temperature differences between sunlit and shadowed regions. Mars, with a rotation period closer to Earth's, experiences more regular day and night cycles. Although still cold overall, the Martian surface does not undergo the same rapid and extreme thermal shifts seen on the Moon. This creates a more predictable, though still harsh, thermal environment. Surface composition plays another important role in defining environmental difficulty. Lunar regolith is sharp, fine, and highly abrasive due to billions of years of micrometeorite impacts without atmospheric erosion. This dust can cling to surfaces and degrade mechanical systems. Mars also has fine dust, but it is influenced by wind and chemical processes that alter its distribution and composition. The presence of oxidized iron compounds gives Mars its characteristic color and introduces different chemical interactions with equipment and potential biological systems. Gravity differences further distinguish the two environments. The Moon has significantly lower gravity compared to Mars, which affects how dust settles, how structures must be anchored, and how human physiology responds over time. Mars, while still lower than Earth, provides a stronger gravitational pull than the Moon, which may reduce some long-term physiological complications associated with extended low-gravity exposure. However, both environments remain outside the range of normal human adaptation without artificial countermeasures. In terms of long-term settlement potential, these baseline differences shape the feasibility of sustained human presence. The Moon presents a more immediate engineering challenge due to its vacuum exposure, radiation intensity, and thermal extremes. Mars presents a more complex environmental system, with atmospheric dynamics, seasonal variability, and potential chemical resources, but still requires protection from radiation and low-pressure conditions. Both environments demand closed life support systems, but the stability and external interaction differ in important ways. At this foundational level of comparison, the Moon appears more hostile in its raw exposure to space conditions, while Mars introduces a layered environment that is less extreme in some respects but more complex in others. These differences form the starting point for deeper examination of how each world interacts with human biology, technology, and long-term survival systems. The environment around both the Moon and Mars is defined not only by distance from the Sun, but by the presence or absence of atmosphere and the resulting pressure conditions that govern every physical interaction at the surface. In this comparison, the concept of vacuum exposure becomes central. A vacuum is a region where particle density is so low that matter behaves differently from any Earth-based experience. On the Moon, this condition dominates completely. There is effectively no atmosphere capable of sustaining pressure-shaping weather or buffering environmental change. Mars, while still extremely thin in atmospheric terms, maintains a measurable layer of gas that alters surface behavior in subtle but important ways. On the lunar surface, the absence of atmospheric pressure means that exposed materials exist in a state of direct contact with space. Human physiology is not adapted to such conditions. Without pressure, bodily fluids would begin to behave differently, with volatile components tending toward vaporization at normal temperatures. This does not mean instantaneous boiling in a violent sense, but it does indicate that liquid stability depends entirely on containment. Any breach in a sealed system would immediately create a hazardous environment for biological tissue. For this reason, survival on the Moon depends entirely on pressurized suits and habitats that replicate Earth-like pressure conditions internally. Mars presents a different situation. Its atmospheric pressure is extremely low compared to Earth, far below what is needed to support unprotected human life. But it is not a complete vacuum. The thin carbon dioxide atmosphere exerts enough force to slightly alter physical behavior at the surface. Although humans still cannot survive without full protection, The presence of this atmosphere means that pressure gradients are less extreme than on the Moon. Structural systems on Mars must still maintain internal pressure, but the difference between inside and outside is marginally less severe, reducing some mechanical stress on habitat walls over long durations. The absence of atmosphere on the Moon also means there is no medium for sound transmission. Vibrations do not propagate through air because there is none present. On Mars, sound can travel, although it behaves differently due to the thin and carbon dioxide-rich composition of the atmosphere. This difference has no direct survival benefit, but it reflects the broader contrast in how physical forces interact with each environment. Thermodynamic behavior is also shaped by the presence or absence of atmospheric particles. On the Moon, heat transfer occurs primarily through radiation. Surfaces exposed to sunlight absorb energy directly and re-emit it into space when shaded. There is no air to distribute heat gradually, so temperature differences can develop quickly between illuminated and shadowed regions. In contrast, Mars has a thin atmosphere that allows limited convection. Although weak, this process distributes heat more evenly across regions, slightly reducing extreme local variation. Pressure stability is another critical factor. On the Moon, pressure is essentially constant at near zero. This means that any artificial environment must be entirely self-contained. Every structure functions as a sealed system against an external void that offers no resistance. On Mars, atmospheric pressure varies slightly with altitude temperature and seasonal carbon dioxide cycles. These variations are small but measurable, and they introduce a dynamic element to surface conditions that does not exist on the Moon. Seasonal changes can cause portions of the atmosphere to freeze at the poles and later sublimate, subtly altering global pressure patterns. The behavior of gases is also fundamentally different between the two environments. On the Moon, released gases do not accumulate. They disperse into space immediately, making long-term atmospheric formation impossible without continuous replenishment. Mars retains its atmosphere despite its thinness, because gravitational retention is sufficient to hold some gases in place over geological timescales. However, the atmosphere is still gradually lost to space through processes such as solar wind stripping, meaning it remains in a delicate balance rather than a stable system. Human engineering must respond directly to these differences. Lunar habitats require complete isolation from external conditions, with redundant sealing systems designed to prevent catastrophic decompression. The margin for error is extremely small because any breach leads to immediate exposure to vacuum. Mars habitats also require sealing, but they must additionally manage interactions with a chemically active atmosphere that can carry fine dust particles and carbon dioxide infiltration. While both environments are hostile, the Moon presents a more absolute boundary between inside and outside, whereas Mars presents a gradient between two low-pressure states. Biological implications of vacuum exposure further highlight the contrast. On the Moon, unprotected exposure would lead to rapid loss of consciousness due to lack of oxygen and pressure support. Cellular structures depend on stable pressure gradients to maintain function, and these gradients collapse in vacuum conditions. Mars still presents an environment where unprotected exposure is lethal, but the presence of some atmospheric pressure slightly delays the rate of physiological collapse. The difference is not sufficient to support survival, but is relevant in understanding the severity of each environment. Another consequence of vacuum conditions is the behavior of volatile compounds in soil and ice. On the Moon, any trapped gases in regolith are easily released into space when disturbed, and water ice, where present in permanently shadowed regions, exists in a highly stable frozen state due to the absence of atmospheric interaction. On Mars, ice can undergo sublimation directly into the thin atmosphere, contributing to seasonal atmospheric changes. This process links surface materials and atmospheric behavior in a way that does not occur on the Moon. From an operational perspective, vacuum conditions also influence maintenance and mechanical reliability. Lubricants, seals, and moving parts behave differently when exposed to near-zero pressure. On the Moon, materials must be carefully selected to avoid outgassing and degradation in vacuum. Mars introduces additional chemical interactions due to the presence of reactive dust and atmospheric components, requiring broader material resilience. At this stage of comparison, vacuum exposure defines the Moon as a world of absolute external emptiness, while Mars represents a world of extremely thin but active atmospheric presence. Both environments require full life support systems for human survival, yet the mechanisms of failure and environmental interaction differ significantly. The Moon imposes immediate and total reliance on containment, while Mars introduces a slightly more moderated but chemically and dynamically active external environment that still remains far beyond natural human tolerance. Radiation in space forms a continuous background condition that shapes the surface environments of both the Moon and Mars. Unlike Earth, neither body has a strong global magnetic field or a thick atmosphere capable of significantly reducing incoming high-energy particles. This absence exposes their surfaces to solar radiation and galactic cosmic rays with only limited natural moderation. The difference between the two worlds lies not in the presence or absence of radiation, but in how each environment slightly modifies its intensity and interaction with matter at the surface. Radiation in this context refers to energetic particles and electromagnetic emissions that originate from the Sun and from distant astrophysical sources. Solar radiation includes steady streams of charged particles known as the solar wind, as well as episodic solar energetic particle events associated with solar flares and coronal mass ejections. Galactic cosmic rays originate outside the solar system and consist of high-energy protons and atomic nuclei that travel through space at nearly relativistic speeds. These particles carry enough energy to alter atomic structures when they collide with matter, producing secondary particles and ionization cascades. On the Moon, radiation reaches the surface almost directly. There is no substantial atmosphere to absorb or scatter incoming particles. The lunar surface is therefore continuously exposed to both steady solar wind and high-energy cosmic rays. The regolith or surface layer of fragmented rock and dust does provide some minimal shielding when particles penetrate below the top layers, but this effect is shallow and limited. Any human presence on the surface would experience direct radiation exposure unless protected by substantial shielding, such as underground habitats or thick material barriers. Mars presents a slightly different radiation environment due to its thin atmosphere. Although this atmosphere is not sufficient to block most high-energy cosmic rays, it does provide partial attenuation of lower-energy solar particles. The atmospheric column above the surface can scatter and absorb some incoming radiation, reducing the intensity of certain events compared to the lunar surface. This effect is not large enough to eliminate risk, but it creates a measurable difference in radiation dose rates between the two environments. The absence of a global magnetic field on both bodies means that charged particles are not deflected in a structured way before reaching the surface. On Earth, the magnetic field channels many particles toward the poles, where they interact with the atmosphere to produce auroras. On the Moon and Mars, no such large-scale deflection occurs, so particle flux depends primarily on direct solar and cosmic exposure. However, localized magnetic anomalies on the Moon can create small regions of reduced particle interaction, though these are not sufficient to provide broad protection. Radiation interacts with biological tissue by ionizing atoms and molecules, disrupting chemical bonds and damaging cellular structures. Over time, this can increase the risk of radiation sickness, genetic mutations, and long-term health effects. The severity of these effects depends on exposure duration, shielding, and particle energy. On the Moon, the lack of atmospheric shielding means that radiation exposure is more direct and less variable. On Mars, the thin atmosphere introduces slight variability, particularly during periods of solar activity when particle flux increases. Solar storms represent one of the most significant radiation hazards for both environments. During such events, large quantities of charged particles are ejected from the Sun and travel through space. When these particles reach the Moon, they impact the surface with minimal interference. On Mars, the atmosphere provides limited buffering, but strong solar storms can still significantly increase surface radiation levels. In both cases, without protective shielding, exposure during such events would be severe. Secondary radiation is another important factor. When high-energy cosmic rays strike the surface of either body, they can produce cascades of secondary particles, including neutrons and gamma rays. These secondary particles can penetrate deeper into materials and contribute to the overall radiation dose. The composition of the lunar regolith and Martian soil influences how these secondary particles are produced and absorbed, but neither environment provides a complete barrier to their propagation. From a long-term habitation perspective, radiation exposure accumulates over time. Even relatively low levels of continuous exposure can become significant over months or years. The Moon, with its more direct exposure profile, presents a higher baseline radiation environment at the surface. Mars, while still hazardous, benefits from partial atmospheric shielding and greater opportunities for subsurface protection due to the presence of ice-rich regions that can be used as shielding material. Subsurface environments on both bodies offer a potential mitigation strategy. Beneath the lunar surface, layers of regolith can significantly reduce radiation levels, especially at depths of a few meters. On Mars, subsurface environments may also provide protection with additional benefits from the presence of ice and sediment layers that can further attenuate radiation. In both cases, moving below the surface transforms the radiation environment from direct exposure to a more controlled and reduced risk setting. Radiation also affects electronic systems and infrastructure. High-energy particles can disrupt circuits, degrade materials, and cause temporary or permanent malfunctions in sensitive equipment. On the Moon, the higher direct flux of radiation increases the importance of hardened electronics and redundant systems. On Mars, similar concerns exist, but the additional atmospheric interaction slightly reduces the frequency of some particle impacts at the surface level. At this stage of comparison, radiation emerges as a shared but uneven hazard. Both the Moon and Mars lack strong natural shielding, but the Moon experiences more direct and consistent exposure due to its absence of atmosphere. Mars introduces a partial buffer that modifies the radiation environment without eliminating its danger. The difference is subtle in physical terms, but significant in long-term survival planning, where even small variations in exposure can accumulate into major health and operational consequences over time. The lunar surface exists under a radiation environment that is shaped by constant exposure to space without meaningful atmospheric interruption. The absence of air and magnetic shielding allows energetic particles from the Sun and beyond the solar system to reach the ground in a direct and unfiltered manner. This creates a surface condition where radiation levels remain relatively steady over time, interrupted only by variations in solar activity. The Moon does not experience weather systems or atmospheric redistribution, so there is no natural mechanism to diffuse or moderate radiation after it arrives. Solar radiation on the Moon includes a continuous flow of charged particles emitted by the Sun. This solar wind interacts directly with the uppermost layer of lunar soil. Because there is no atmosphere to slow or scatter these particles, their energy is deposited directly into surface materials. Over long periods, this interaction alters the chemical structure of the regolith, creating radiation-damaged grains and implanted particles. These changes accumulate gradually and remain preserved due to the absence of erosion or atmospheric recycling. During periods of heightened solar activity such as solar storms, the radiation environment becomes significantly more intense. Large bursts of energetic particles can reach the lunar surface within hours. Without atmospheric shielding, these events impact all exposed regions simultaneously. The lack of a protective atmospheric layer means that the surface experiences full exposure, with only minor variations caused by local terrain or depth beneath the soil. Even shallow burial under regolith provides only partial reduction in exposure, as high-energy particles can penetrate several centimeters or more depending on their energy. Galactic cosmic rays contribute a persistent background of high-energy radiation. These particles originate from outside the solar system and travel at extremely high speeds. When they strike the lunar surface, they generate cascades of secondary particles, including neutrons and gamma radiation. These secondary effects extend the reach of radiation beyond the initial impact point, allowing energy to propagate deeper into the soil. Over time, this contributes to a complex radiation field beneath the surface that is not limited to direct particle impact. The lunar regolith plays a limited role in moderating radiation exposure. It is composed of fragmented rock formed by billions of years of micrometeorite impacts. While it can absorb and scatter some incoming particles, its effectiveness is shallow and depends strongly on depth. A thin layer provides minimal protection, while deeper layers offer improved shielding. However, even at moderate depths, high-energy cosmic rays can still penetrate, meaning that complete protection requires substantial burial or engineered shielding. The absence of atmospheric weathering also means that radiation effects accumulate without interruption. On Earth, atmospheric processes continuously reshape and recycle surface materials, redistributing energy and chemical changes over time. On the Moon, once radiation alters a material, that change remains largely permanent. This leads to a surface environment where radiation damage is effectively preserved in place, creating a long-term record of exposure. Thermal conditions interact indirectly with radiation exposure. The Moon's surface experiences extreme temperature shifts between lunar day and night. These cycles can influence how materials respond to radiation by affecting their structural stability. During hot periods, certain materials may become more reactive, while during cold periods they become more brittle. Although these effects do not reduce radiation intensity, they modify how radiation damage manifests in the regolith over time. The lack of atmosphere also means that secondary particles generated by cosmic ray interactions are not significantly absorbed before reaching the surface. On Earth, atmospheric depth plays a major role in breaking down high-energy particles before they reach ground level. On the Moon, this shielding effect is absent, allowing secondary radiation cascades to reach deeper into the surface layers with relatively little attenuation. From a human exposure perspective, the lunar radiation environment is highly direct. Any surface activity would result in continuous exposure to both primary and secondary radiation sources. The absence of atmospheric fluctuation means that radiation levels are predictable but consistently elevated compared to more shielded environments. Protective strategies must therefore rely entirely on artificial shielding, subsurface habitation, or carefully timed surface operations. Instrumental measurements from lunar missions have confirmed that radiation levels on the Moon are significantly higher than on Earth. Dosimetry data collected on and around the lunar surface indicates exposure rates that would exceed safe limits for long-term human presence without shielding. These measurements are consistent with the expected effects of an unprotected surface, exposed to solar and galactic radiation without atmospheric moderation. The interaction between radiation and the lunar environment extends beyond biological concerns. Electronic systems operating on the surface must also be designed to withstand high-energy particle impacts. Radiation can cause temporary disruptions in electronic circuits or permanent damage to sensitive components. This necessitates hardened designs and redundancy in systems intended for extended lunar operation. At this stage of analysis, the Moon's radiation environment can be understood as a direct extension of space itself onto a solid surface. There is no meaningful separation between space radiation and ground-level conditions. The surface effectively functions as an exposed interface with the solar system's energetic particle environment, shaped only minimally by local soil depth and composition. Mars, in contrast, will later be seen to introduce a thin atmospheric layer that slightly modifies this interaction, but on the Moon no such moderation exists. The result is a radiation environment that is constant, direct, and largely unchanged by surface processes, making it one of the most exposed planetary surfaces in the inner solar system. Mars presents a radiation environment that is still severe by Earth standards, yet it differs from the lunar surface through the presence of a thin atmospheric layer that slightly modifies how energetic particles interact with the ground. This atmosphere is composed mainly of carbon dioxide and extends outward in a diffuse envelope that is far less dense than Earth's, but still capable of producing measurable effects on incoming radiation. Unlike the Moon, where space conditions reach the surface without interruption, Mars introduces a transitional medium that partially reshapes the energy and distribution of particle impacts. As solar particles approach Mars, they first encounter this tenuous atmospheric layer. The interaction does not fully block or absorb high-energy radiation, but it does cause partial scattering and energy loss, especially for lower-energy particles. This means that some portion of solar wind and solar energetic particles is reduced in intensity before reaching the ground. The effect is not uniform and it varies with atmospheric density, which itself changes with altitude, season, and temperature. During colder periods, carbon dioxide can condense at the poles, slightly thinning the atmosphere elsewhere and reducing its shielding effect. Galactic cosmic rays, which are much more energetic than most solar particles, are far less affected by Mars' atmosphere. These particles penetrate deeply through atmospheric layers and continue to interact with the surface almost as directly as they do on the Moon. However, the atmosphere still plays a role in generating secondary particle cascades at higher altitudes, which can slightly alter the distribution of radiation reaching the ground. These cascades include neutrons and other secondary particles that contribute to the overall radiation environment experienced at the surface. The Martian atmosphere also introduces variability in radiation exposure over time. Because atmospheric density is not constant, the degree of shielding changes depending on seasonal cycles and dust activity. When dust is suspended in the atmosphere, it can influence temperature and circulation patterns, which in turn affect atmospheric thickness. This creates subtle fluctuations in radiation levels that are not present on the Moon, where conditions remain more stable and direct. Surface pressure on Mars is still extremely low, but it is sufficient to allow some interaction between atmospheric particles and incoming radiation. This interaction reduces the sharpness of radiation peaks during certain solar events. On the Moon, solar storms reach the surface with nearly full intensity. On Mars, the atmosphere absorbs and disperses a portion of the energy, slightly reducing peak exposure levels. However, during major solar storms, this shielding effect becomes less significant and radiation levels can still rise sharply. The presence of an atmosphere also affects how secondary radiation behaves. When cosmic rays strike atmospheric molecules, they can produce cascades of secondary particles before reaching the surface. This means that radiation is not only reduced in some cases, but also redistributed in energy form. Some particles lose energy and dissipate higher in the atmosphere, while others reach the ground with altered trajectories and reduced intensity. This layered interaction creates a more complex radiation profile compared to the Moon's direct exposure. Unlike Earth, Mars does not have a strong global magnetic field to deflect charged particles. As a result, the atmosphere acts as the primary moderating factor. This makes the Martian radiation environment dependent on atmospheric conditions rather than magnetic protection. The absence of a magnetic field means that polar and equatorial regions receive broadly similar radiation exposure, although local atmospheric variations can still introduce small differences. From a biological perspective, the partial shielding provided by the Martian atmosphere slightly reduces long-term radiation dose compared to the lunar surface. However, the reduction is not sufficient to eliminate health risks. Human exposure on Mars would still exceed safe levels without additional shielding. The atmosphere reduces some of the lower energy particle flux, but high-energy cosmic rays remain a dominant hazard. Subsurface environments on Mars become particularly important in this context. Because the atmosphere provides only partial protection, deeper layers of soil or ice offer more reliable shielding against radiation. The combination of atmospheric moderation and subsurface protection creates a layered defense system that is absent on the Moon. This makes buried habitats or lava tubes on Mars comparatively more effective in reducing radiation exposure than shallow surface structures. Electronic systems on Mars also benefit slightly from atmospheric shielding. The reduction in lower energy particle flux decreases the frequency of minor radiation-induced disturbances in sensitive electronics. However, high-energy events still pose significant risks, and systems must still be hardened against single-event effects caused by cosmic rays and secondary particle showers. The Martian atmosphere also interacts with radiation in ways that can influence atmospheric chemistry. High-energy particles can break molecular bonds in carbon dioxide, producing reactive species that may participate in further chemical reactions. These processes contribute to a dynamic but thin atmospheric chemistry that does not exist on the Moon. Although these reactions are limited in scale, they demonstrate that Mars has an active interaction between radiation and atmospheric composition. At a broader level, the comparison between Mars and the Moon in terms of radiation exposure highlights a key distinction. The Moon represents a direct interface with space radiation, where energetic particles reach the surface with minimal modification. Mars represents a partially mediated environment where a thin atmosphere introduces scattering, absorption, and redistribution of energy. Neither environment provides sufficient natural protection for unassisted human survival, but the mechanisms of exposure differ in structure and variability. At this stage of analysis, Mars can be understood as a world where radiation is still a dominant constraint, yet it is filtered through a fragile atmospheric system that slightly reshapes its intensity and behavior. This makes its surface environment less directly exposed than the Moon, but still fundamentally hostile without engineered protection. Temperature on the lunar surface is governed almost entirely by direct solar radiation and the absence of any atmosphere capable of distributing or retaining heat. Without air to carry energy between regions, heat transfer occurs primarily through radiation and limited conduction within the soil. This creates a surface environment where temperature is not moderated by weather, wind, or atmospheric mixing. Instead, each location responds almost independently to sunlight and shadow, producing sharp contrasts across short distances and time periods. During lunar daylight, sunlight strikes the surface with full intensity. The lack of atmospheric scattering means that incoming solar energy reaches the ground in a concentrated form. The regolith absorbs this energy and warms significantly. Because there is no atmosphere to redistribute heat, the warming remains localized to the sunlit surface layers. Deeper layers remain relatively insulated, creating strong vertical temperature gradients within the soil. This layered thermal structure reflects the absence of convection and atmospheric conduction. When the sun sets on the lunar surface, the transition to darkness is abrupt. Without an atmosphere to retain heat or gradually release stored energy, the surface begins to cool rapidly. Heat is lost directly to space through radiation. This process is efficient in the vacuum environment, allowing temperatures to drop quickly compared to any Earth-based environment. The result is a strong contrast between daytime and nighttime conditions, with extreme differences developing over the course of a single lunar cycle. This slow rotation of the Moon relative to its orbital period around Earth contributes to the duration of these thermal cycles. Each lunar day and night lasts for an extended period, allowing temperatures to remain at extreme highs or lows for prolonged durations. This extended exposure intensifies thermal stress on materials and any potential biological systems. Surfaces exposed to sunlight undergo long heating periods, while shadowed regions experience equally long cooling periods without interruption. In permanently shadowed regions such as deep craters near the lunar poles, sunlight never reaches the surface. These areas remain in continuous darkness and can reach extremely low temperatures. Without atmospheric heat transfer, these regions become cold traps where volatile substances including water ice can remain stable over long periods. The absence of atmospheric circulation ensures that heat does not easily migrate into these areas, preserving their low temperature state. Conversely, equatorial and sun-facing regions experience intense heating during lunar daytime. The regolith in these areas can reach temperatures high enough to affect material stability and mechanical performance. The combination of high peak temperatures and rapid cooling creates repeated thermal cycling stress, which can gradually degrade materials through expansion and contraction. Over long periods, this process contributes to the breakdown of exposed structures and natural surfaces alike. Mars, in contrast, experiences a different thermal regime due to the presence of a thin atmosphere. Although this atmosphere is not dense enough to provide strong insulation, it still allows for limited heat transfer through convection. This moderates temperature differences between day and night compared to the Moon. Heat absorbed during the day can be partially redistributed by atmospheric motion, reducing the severity of localized extremes. The Martian atmosphere also introduces seasonal temperature variation, driven by changes in solar exposure and atmospheric carbon dioxide behavior. During colder seasons, carbon dioxide can freeze at the poles, temporarily reducing atmospheric density and altering thermal dynamics. During warmer periods, sublimation of frozen carbon dioxide returns gas to the atmosphere, increasing its density and slightly enhancing heat distribution. These cycles introduce variability that is absent on the Moon's more static thermal environment. Despite this moderation, Mars remains a cold environment overall. Its greater distance from the Sun compared to Earth means that baseline solar energy input is lower. As a result, even with atmospheric effects, surface temperatures remain significantly below Earth-like conditions. However, the key distinction lies not in absolute temperature, but in the rate and range of variation. Mars exhibits slower and more gradual thermal transitions compared to the rapid extremes of the Moon. The thermal properties of surface materials also influence environmental behavior. Lunar regolith has low thermal conductivity, meaning it does not efficiently transfer heat between layers. This contributes to sharp surface-level temperature changes, while deeper layers remain insulated. On Mars, soil and dust layers interact with the atmosphere, allowing for slightly more uniform heat distribution over time, although still limited by low atmospheric density. Thermal inertia. The ability of a material to resist changes in temperature plays a significant role in both environments. On the Moon, low thermal inertia at the surface leads to rapid heating and cooling cycles. On Mars, variations in dust content, soil composition, and atmospheric interaction produce a more complex but still relatively low thermal inertia system. These differences affect how quickly environments respond to changes in sunlight exposure. For human habitation, these thermal differences have direct implications. On the Moon, habitats must withstand extreme and rapid temperature swings between prolonged day and night periods. On Mars, temperature management still requires insulation and heating systems, but the external fluctuations are less abrupt. This reduces some engineering stress, although not enough to eliminate the need for robust thermal control systems. At this stage of comparison, the Moon represents an environment of extreme thermal instability, driven by direct exposure to space and the absence of atmospheric moderation. Mars represents a colder but more thermally moderated environment, where a thin atmosphere slightly smooths temperature transitions. Both remain far outside naturally habitable conditions, yet the mechanisms of thermal behavior differ significantly, shaping how each world challenges any attempt at long-term presence. Mars presents a thermal environment shaped by a thin atmosphere that, while weak, introduces a measurable buffering effect on surface temperatures. This atmosphere allows limited convection, meaning heat can move through gas motion, rather than relying entirely on radiation and conduction. As a result, temperature changes across the Martian surface tend to occur more gradually than on the Moon, where no atmospheric medium exists to redistribute energy. This difference creates a distinct contrast in how both worlds respond to solar heating and nighttime cooling. During the Martian day, sunlight passes through the thin carbon dioxide atmosphere and reaches the ground with reduced scattering compared to Earth, but still with some atmospheric interaction. The surface absorbs this energy and warms, but a portion of the heat is transferred into the surrounding air. Because the atmosphere is not dense, this transfer is limited, yet it is sufficient to prevent the most extreme localized heating seen on the lunar surface. Heat stored in the ground can also be partially released back into the atmosphere, where weak winds distribute it across regions. At night, Mars cools as it loses heat to space, but the atmosphere slows this process slightly by retaining some thermal energy and redistributing it over the surface. This creates a less abrupt transition between day and night compared to the Moon, where temperature drops occur rapidly due to direct radiation into space. The Martian atmosphere acts as a thin thermal blanket, not strong enough to stabilize the climate fully, but enough to reduce the sharpness of extremes. Seasonal variation plays a major role in Martian temperature behavior. The planet's axial tilt produces changes in sunlight distribution over the course of its orbit around the Sun. These seasonal cycles are similar in principle to those on Earth, but occur in a colder and thinner atmospheric context. As seasons shift, atmospheric carbon dioxide can condense at the poles during winter, temporarily reducing atmospheric pressure across the planet. When temperatures rise again, this frozen carbon dioxide sublimates back into gas, increasing atmospheric density and slightly enhancing thermal buffering. These seasonal pressure changes influence not only temperature stability, but also wind patterns and dust activity. Although dust is not the focus of radiation or atmospheric shielding, it plays an indirect role in thermal behavior. Suspended dust can absorb sunlight and redistribute heat within the atmosphere, contributing to regional temperature variations. This process creates a feedback system where temperature, atmospheric density, and surface dust interact in a continuously shifting balance. Despite these moderating effects, Mars remains a cold environment. Average surface temperatures are far below those of Earth, and many regions experience prolonged freezing conditions. However, the key distinction lies in variability rather than absolute temperature alone. The Martian surface does not typically experience the same rapid thermal collapse seen on the Moon after sunset. Instead, temperature changes unfold over longer periods, allowing for more gradual environmental transitions. On the Moon, the absence of atmosphere means that once sunlight disappears, heat escapes almost directly into space. There is no medium to retain or redistribute energy, so cooling is immediate and intense. Mars, even with its thin atmosphere, retains a small amount of heat within the air itself. This retained energy slows the cooling process and creates a more continuous thermal gradient between illuminated and shadowed regions. Thermal interaction with the surface also differs between the two environments. Martian soil interacts with the atmosphere, allowing limited heat exchange through gas conduction. Although weak, this interaction helps reduce extreme surface temperature spikes. On the Moon, heat remains confined to direct radiation and solid conduction within the regolith, leading to sharper contrast between exposed and shaded areas. The presence of an atmosphere also allows for weak but persistent wind activity on Mars. These winds contribute to horizontal heat redistribution, moving warmer air from sunlit regions toward cooler areas. While not strong enough to create Earth-like weather systems, this circulation still plays a role in smoothing temperature differences over time. The Moon lacks any comparable mechanism, leaving each region thermally isolated except for slow conduction through the ground. From an engineering perspective, these differences influence habitat design and energy management. On Mars, structures must still be heavily insulated, but they benefit from a slightly more stable external environment. Thermal loads change more gradually, allowing systems to respond with less abrupt stress. On the Moon, habitats must endure extreme and rapid transitions between heat and cold, requiring more aggressive thermal control and energy storage solutions. Biologically, thermal stability is critical for any form of sustained human presence. The Martian environment, while still far outside human tolerance without protection, offers a slightly less volatile thermal regime. The Moon presents a more immediate and extreme challenge due to its lack of atmospheric moderation. In both cases, survival depends entirely on artificial environments, but the degree of external thermal variability differs significantly. At this stage of comparison, Mars can be understood as a planet where temperature is shaped by a fragile but active atmosphere that introduces limited moderation and variability over time. The Moon, by contrast, remains a body where thermal conditions are governed almost entirely by direct solar exposure and vacuum cooling. These differences define two distinct types of environmental stress, both severe but structured in fundamentally different ways. The surface of the Moon is covered by a layer of fragmented rock and dust known as regolith, formed over billions of years through continuous micrometeorite impacts. In the absence of an atmosphere, even the smallest particles of space debris strike the surface at high velocity, breaking down solid rock into increasingly fine grains. This process produces a material that is sharp, abrasive, and highly reactive to mechanical disturbance. Unlike Earth soil, it contains no organic content and has never been softened by wind or water erosion. Every grain reflects a long history of impact-driven fragmentation. The absence of atmospheric weathering means that lunar dust remains angular rather than rounded. On Earth, wind and water gradually smooth particles, reducing their abrasiveness over time. On the Moon, no such processes exist, so the regolith retains jagged edges at microscopic scales. This makes it particularly harsh when interacting with mechanical systems or human equipment. The dust can infiltrate joint seals and filters, gradually degrading performance through physical abrasion rather than chemical reaction. When disturbed, lunar regolith behaves in ways that are difficult to manage. The fine particles are easily lofted into suspension by mechanical activity, not by wind but by direct physical force. In a vacuum environment, these particles do not settle in the same way they would in an atmosphere. Instead, they follow ballistic trajectories and can adhere to surfaces due to electrostatic charging. This electrostatic behavior arises from constant exposure to solar radiation and particle impacts which charge the surface materials unevenly. Mars also has a significant dust component, but its origin and behavior differ due to the presence of a thin atmosphere. Martian dust is finer and more globally distributed, shaped by wind-driven erosion and atmospheric circulation. Unlike lunar regolith, which is primarily the product of impact fragmentation, Martian dust also undergoes chemical alteration. The presence of oxygen-bearing compounds and oxidizing processes gives Martian soil a distinct reddish color and changes its chemical reactivity. On Mars, dust can remain suspended in the atmosphere for extended periods due to low gravity and weak atmospheric density. This leads to large-scale dust storms that can cover vast regions of the planet. These storms are driven by solar heating and atmospheric dynamics, allowing dust to circulate and redistribute across the surface. In contrast, the Moon experiences no atmospheric transport, so dust movement remains highly localized and dependent on mechanical disturbance. The interaction between dust and equipment presents different challenges in each environment. On the Moon, dust is sharp, adhesive, and persistent in its attachment to surfaces. It can accumulate on spacesuit seals and optical systems, reducing efficiency and increasing wear. Because there is no atmosphere to carry it away once dust is deposited, it tends to remain in place unless actively removed. This creates long-term contamination issues for any surface operation. On Mars, dust infiltration occurs through atmospheric processes. Fine particles can enter mechanical systems carried by wind, and they can settle over time across exposed surfaces. While the particles may be less angular than lunar dust, their chemical composition can introduce additional challenges, including corrosion or coating of surfaces. The atmosphere also allows dust to be transported over long distances, meaning contamination can be widespread rather than localized. Electrostatic charging is particularly significant on the Moon. The lack of atmospheric humidity and continuous exposure to solar radiation allows surfaces to accumulate charge differentials. Dust particles can become electrically attracted to surfaces, causing them to cling tightly to equipment. This effect complicates removal and increases the persistence of contamination. On Mars, atmospheric particles can also carry charge, but the presence of gas molecules and occasional humidity effects reduce the intensity of electrostatic adhesion compared to the lunar surface. From a human operational perspective, dust on the Moon presents immediate mechanical and biological concerns. Fine particles can penetrate seals in protective suits, leading to abrasion of internal components. Inhalation risk is mitigated by sealed systems, but contamination of external interfaces remains a persistent problem. The sharpness of the particles increases the potential for long-term wear on materials, especially in moving parts. On Mars, dust poses a different type of risk. While less mechanically abrasive, it can accumulate over time on solar panels, reducing energy efficiency. Atmospheric storms can rapidly reduce visibility and coat exposed surfaces in fine layers of material. This introduces operational uncertainty, as environmental conditions can change over large areas in relatively short periods of time compared to the Moon's static surface environment. Thermal and radiation interactions also influence dust behavior. On the Moon, dust is exposed to extreme temperature cycles and constant radiation bombardment, which may alter its surface properties over time. On Mars, dust interacts with a chemically active atmosphere and experiences seasonal changes in pressure and temperature. leading to a more dynamic but less mechanically harsh evolution. At this stage of comparison, the lunar environment presents a surface material that is static sharp and mechanically aggressive, shaped entirely by impact history and vacuum exposure. Mars presents a more active dust system, shaped by atmosphere, wind, and chemical processes. Both environments create significant challenges for human technology, but the mechanisms of degradation and movement differ fundamentally between a static abrasive layer and a dynamic atmospheric system. The Martian atmosphere, though thin, is active enough to support large-scale dust transport across the planet's surface. This creates one of the most visually and physically significant environmental phenomena on Mars, in the form of dust storms that can range from local disturbances to planet-encircling events. These storms are driven by temperature differences between the surface and atmosphere, combined with seasonal changes in solar heating that alter wind patterns and atmospheric circulation. Unlike the Moon, where the absence of atmosphere prevents any weather systems, Mars exhibits a dynamic system of airborne particles that continuously reshape surface conditions. As sunlight heats the Martian surface, air near the ground warms and begins to rise. Because the atmosphere is thin, even small temperature differences can generate wind movement. These winds lift fine dust particles from the surface, especially in regions where the soil is already loosely bound. Once suspended, the dust interacts with sunlight and atmospheric motion, absorbing and redistributing heat. This process can reinforce the initial temperature differences, strengthening wind activity and allowing storms to expand. Local dust storms can form frequently, and may last for hours or days. These smaller events are limited in scale, but demonstrate the constant interaction between surface and atmosphere. Under certain conditions, multiple local storms can merge, expanding their reach. When this occurs on a large enough scale, regional storms can evolve into planetary events that envelop the entire planet in a thick layer of airborne dust. During such global storms, sunlight reaching the surface is significantly reduced, and surface conditions change across vast areas. The most significant effect of these dust storms is the reduction of solar energy reaching the ground. Dust suspended in the atmosphere scatters and absorbs sunlight, reducing surface illumination. This leads to cooling at the surface, while the atmosphere above may retain heat, absorbed by dust particles. The result is a vertical redistribution of thermal energy, which can alter atmospheric circulation patterns and extend the duration of storm conditions. During large-scale storms, the Martian surface can experience prolonged periods of reduced sunlight. This has important implications for any systems that rely on solar energy. The Moon does not experience this type of atmospheric variability, as there is no medium to carry or suspend particles. On Mars, however, dust storms introduce a temporal layer of unpredictability to surface conditions, where visibility, temperature, and energy availability can change significantly over time. The behavior of dust in Martian storms is influenced by the planet's low gravity and thin atmosphere. Particles can remain suspended for extended periods because settling is slow and atmospheric turbulence is sufficient to keep them aloft. This creates a feedback loop where dust both influences and is influenced by atmospheric motion. The longer dust remains in the atmosphere, the more it affects temperature gradients and wind patterns, sustaining storm conditions. Unlike Earth storms, Martian dust storms do not involve liquid water or precipitation. Instead, they are entirely driven by dry particle dynamics. This makes them fundamentally different from terrestrial weather systems. The energy driving these storms comes primarily from solar heating of the surface and atmosphere rather than moisture-driven atmospheric instability. This distinction highlights the unique nature of Martian meteorology, which operates under conditions of low pressure and limited atmospheric density. On the Moon, no comparable system exists. Without an atmosphere, there is no mechanism for particle suspension or transport over large distances. Dust remains localized unless physically disturbed. As a result, the lunar surface is static in terms of atmospheric dynamics, with no storms, winds, or weather cycles to redistribute material or energy. This absence creates a fundamentally different environmental experience compared to Mars, where atmospheric motion plays an active role in shaping surface conditions. Martian dust storms also affect thermal behavior. As dust particles absorb solar radiation, they heat the surrounding atmosphere. This can reduce temperature differences between the surface and air, temporarily stabilizing certain atmospheric layers. However, once the storm dissipates, the redistribution of dust can lead to new temperature gradients and renewed atmospheric motion. This cyclical interaction creates a complex and evolving system of thermal and particulate exchange. From an operational perspective, dust storms introduce significant variability in surface conditions. Visibility can decrease dramatically during large events, and surface operations must account for changing atmospheric opacity. The accumulation of dust on equipment can also affect mechanical and energy systems. These effects are not permanent, but can recur frequently depending on seasonal and regional atmospheric conditions. The Moon, lacking any atmosphere, avoids these types of dynamic disturbances entirely. However, this stability comes at the cost of environmental predictability only in a static sense. While Mars experiences changing conditions over time, the Moon remains consistently exposed to space without atmospheric variation. Both environments present challenges, but they differ fundamentally in whether those challenges are dynamic or constant. At this stage of comparison, Mars emerges as a world where atmospheric motion, even in a thin form, introduces a layer of environmental complexity that does not exist on the Moon. Dust storms act as a central mechanism linking surface atmosphere and solar energy into a single interacting system. The Moon, by contrast, remains isolated from such interactions, existing in a state where surface conditions are shaped only by direct exposure to space rather than atmospheric processes. Gravity on the Moon and Mars shapes every aspect of human adaptation, from bodily function to long-term structural design, because it determines how matter behaves over extended periods in a low-gravity environment. On the Moon's surface, gravity is significantly weaker than on Earth, creating a condition where weight is reduced to a fraction of familiar experience. Mars provides stronger gravity than the Moon, though still below Earth's level, resulting in a different balance between biological strain and environmental stability. These differences influence not only movement and physical effort, but also the long-term behavior of fluids, tissues, and mechanical systems. In the lunar environment, reduced gravity alters how the human body maintains internal balance. Blood distribution, muscle load, and bone density all respond to the reduced downward force. Over time, the absence of normal gravitational stress leads to gradual weakening of skeletal structure and muscle mass, unless countermeasures are applied. This effect is not unique to the Moon, but it becomes more pronounced due to the combination of low gravity and prolonged exposure in a confined artificial habitat where natural movement is limited. Fluid behavior also changes significantly under lunar gravity. In a low-gravity environment, liquids do not settle in the same way as on Earth. Surface tension becomes more dominant relative to weight, leading to different movement patterns in bodily fluids and mechanical systems. This affects everything from circulation to waste management in closed habitats. Without careful system design, fluids may distribute unevenly, requiring engineered solutions to maintain stability and function. Mars, with its stronger gravitational pull, provides a more familiar mechanical environment for the human body. Although still lower than Earth, Martian gravity allows fluids and tissues to behave in a more Earth-like manner compared to the Moon. This reduces some of the physiological stress associated with long-term low-gravity exposure. Bone and muscle degradation still occur, but at a slower rate compared to lunar conditions. This difference becomes significant over extended periods where cumulative biological effects determine overall habitability. The structural implications of gravity also differ between the two environments. On the Moon, lower gravity reduces the load on buildings and mechanical systems, allowing for lighter structural designs. However, this advantage is offset by the need to withstand vacuum conditions and extreme temperature cycles. Mars with higher gravity requires stronger structural support, but benefits from a more stable external environment in terms of pressure and thermal interaction. This creates a trade-off between mechanical load and environmental harshness. Movement across the lunar surface is also affected by low gravity. Human locomotion behaves differently with longer airborne phases during steps and reduced frictional grounding. This can make movement efficient in some cases, but unstable in others, particularly when interacting with uneven terrain. On Mars, movement is closer to Earth-like walking dynamics, although still altered by reduced weight and surface conditions. The presence of a thin atmosphere does not significantly affect locomotion, but gravity remains the dominant factor. Dust behavior is also influenced by gravity differences. On the Moon, fine particles disturbed by movement can travel further and remain suspended in low trajectories due to weaker gravitational pull. On Mars, slightly stronger gravity causes dust to settle more quickly, although atmospheric motion can counteract this effect by keeping particles suspended in storms or wind currents. This interaction between gravity and atmosphere creates different patterns of surface contamination and redistribution. Fluid systems within habitats must also account for gravitational differences. On the Moon, pumping and containment systems must be carefully engineered to manage fluid separation and movement under reduced gravity. On Mars, fluid behavior is closer to Earth-based engineering expectations, although still requiring adjustment for lower gravitational force. This makes system design on Mars somewhat more intuitive, even if environmental conditions remain harsh. Biologically, gravity also influences long-term adaptation. The human body evolved under Earth's gravitational conditions, meaning both lunar and Martian environments impose stress on musculoskeletal and cardiovascular systems. The Moon presents a stronger deviation from Earth gravity than Mars, resulting in more pronounced adaptation challenges. Mars, while still outside normal human experience, offers a partial intermediate environment that reduces the severity of some gravitational effects. From a long-term habitation perspective, gravity becomes a key factor in determining sustainability. The Moon's lower gravity reduces structural demands but increases biological strain. Mars provides higher gravity that better supports human physiology but requires stronger infrastructure. Neither environment matches Earth's balance, but the degree of deviation differs in ways that directly affect survival strategies and system design. At this stage of comparison, gravity emerges as a fundamental environmental variable that shapes both biological and engineering constraints. The Moon represents a deeper departure from Earth-like gravitational conditions, while Mars offers a partial intermediate state that moderates some long-term physiological risks. Both remain hostile, but they impose different kinds of stress that accumulate in distinct ways over time. Resource availability on the lunar surface is defined by scarcity and isolation. The Moon has no active atmosphere, no liquid water cycle, and no ongoing geological processes that replenish surface materials in a way accessible to human use. Its environment is largely static, shaped by ancient impacts and slow space weathering. This creates a setting where any usable resource must already exist in place or be imported from outside. The absence of continuous replenishment makes long-term sustainability dependent on careful extraction and recycling within a closed system. Water on the Moon exists primarily in the form of ice trapped in permanently shadowed regions near the poles. These regions never receive direct sunlight due to the angle of illumination and the depth of certain craters. In these cold traps, temperatures remain extremely low, allowing volatile compounds to remain stable over long periods. However, this water is not evenly distributed, and its accessibility depends on location depth and extraction technology. Outside these regions, the lunar surface is extremely dry with no atmosphere to sustain liquid or vapor water. The regolith contains small amounts of chemically bound oxygen within mineral structures. This oxygen is not freely available, but can potentially be extracted through chemical processing. Such processes require significant energy input, because the chemical bonds in lunar minerals are stable and resistant to breakdown. Hydrogen is far less abundant on the lunar surface, meaning that key elements for life support systems must often be imported or carefully recycled within closed habitats. Mars presents a different resource environment. Although still harsh, it contains more diverse and accessible materials. One of the most important differences is the widespread presence of water ice beneath the surface and in polar regions. Unlike the Moon's highly localized ice deposits, Martian water ice is more broadly distributed and can be accessed in multiple regions. This provides a more consistent potential source of water for human use, including drinking, agriculture, and fuel production. The Martian atmosphere also contains carbon dioxide in abundance. This gas can be processed to produce oxygen and fuel through chemical reactions. While energy-intensive, these processes benefit from the constant availability of atmospheric input. On the Moon, the absence of an atmosphere means that carbon-based resources must be sourced from regolith, or imported, limiting flexibility in resource utilization. Mineral resources on both bodies are present but differ in accessibility. The Moon's surface is composed of silicate-rich material that has been extensively fragmented by impacts. These minerals can be used for construction and shielding, but require processing. Mars also contains silicate minerals along with iron-rich compounds that give the planet its characteristic color. These materials can potentially support construction and manufacturing, although extraction would still require significant industrial capability. Energy availability is another critical aspect of resource evaluation. The Moon experiences long periods of sunlight and darkness due to its slow rotation, which affects the stability of solar power generation. Extended night periods require energy storage systems or alternative power sources. Mars has a more regular day-night cycle, which allows for more consistent solar energy collection, although dust storms can significantly reduce solar input during certain periods. The stability of resources is also influenced by environmental conditions. On the Moon, resources remain largely unchanged over time due to the lack of atmospheric or geological activity. This makes deposits stable, but also static and difficult to renew. On Mars, atmospheric and seasonal processes can redistribute materials, making some resources more dynamic, but also more variable in accessibility. Subsurface environments play an important role in both locations. On the Moon, subsurface regolith may contain trapped volatiles and provides a stable environment for resource extraction and storage. On Mars, subsurface ice layers and sediment deposits offer more extensive potential for sustained resource use. These underground regions also provide additional protection from radiation, linking resource access with habitat safety. From a logistical perspective, resource scarcity on the Moon creates a stronger dependence on closed-loop systems, where water, air, and materials must be continuously recycled with minimal loss. Mars allows for partial supplementation from local sources, reducing but not eliminating the need for recycling. This difference has significant implications for long-term settlement planning and infrastructure design. At this stage of comparison, the Moon represents a resource environment defined by extreme limitation and isolation, where essential materials exist in restricted and difficult-to-access forms. Mars represents a more chemically and physically diverse environment, where resources are still limited but more broadly distributed and partially replenished through atmospheric and subsurface processes. Both remain far from naturally self-sustaining, but their resource structures differ in availability, accessibility, and long-term usability. Resource potential on Mars is shaped by a combination of subsurface ice deposits, a reactive atmosphere, and geological diversity that extends beyond the immediate surface layer. Unlike the Moon, where most resources are locked in ancient static regolith, Mars presents a system where materials can exist in multiple physical states and can shift slowly through seasonal and environmental cycles. This creates a more varied but still challenging environment for long-term extraction and utilization. One of the most important resources on Mars is water ice. It exists not only in polar caps but also in mid-latitude subsurface regions, where it's protected from rapid sublimation by layers of dust and soil. This distribution is more extensive than the localized ice deposits found on the Moon. The presence of subsurface ice allows for potential extraction in multiple regions, reducing dependence on a single geographic location. This ice can support life support systems, agriculture, and fuel production through chemical processing. The Martian atmosphere, composed mostly of carbon dioxide, provides another key resource. Although thin, it is continuously present and can be used as a raw material for chemical conversion processes. Carbon dioxide can be transformed into oxygen and hydrocarbons through energy-intensive reactions. This gives Mars a partial advantage in terms of in situ resource utilization, as it allows at least one essential gas to be harvested directly from the environment. The Moon lacks this option entirely due to its near-complete absence of atmosphere. Mineral resources on Mars are influenced by both volcanic history and surface oxidation processes. Iron-rich compounds are widespread, giving the planet its characteristic reddish appearance. These materials can potentially be used for construction manufacturing and chemical processing. Basaltic rock formations formed by ancient volcanic activity also provide structural materials that can be processed into building components. The diversity of geological history on Mars creates a broader range of accessible raw materials compared to the Moon's more uniform impact-shattered regolith. Seasonal cycles on Mars also influence resource accessibility. During colder periods, carbon dioxide freezes at the poles, temporarily removing it from the atmosphere and depositing it as solid ice. When temperatures rise, this carbon dioxide sublimates back into gas, returning to the atmospheric system. This cycle creates a dynamic exchange between solid and gaseous states that can be potentially harnessed for storage and extraction strategies. The Moon does not exhibit comparable seasonal resource cycling due to its lack of atmosphere and axial environmental variation at the same scale. Energy availability plays a critical role in determining how effectively these resources can be used. Mars receives less solar energy than Earth due to its greater distance from the Sun, but its regular day-night cycle allows for predictable energy patterns. However, dust storms can reduce solar input significantly by blocking sunlight over large areas. This introduces variability into energy-dependent resource processing systems. On the Moon, solar energy is more intense during daylight periods, but is interrupted by long nights, creating a different kind of energy instability. The subsurface environment of Mars is particularly important for resource stability. Beneath the surface, temperatures are more stable, and ice deposits remain protected from direct atmospheric interaction. These regions may also contain chemically altered minerals formed through long-term interaction with water and volcanic activity. This increases the potential for extracting not only basic elements, but also compounds that could support industrial processes. In contrast, lunar resources are largely confined to surface and near-surface materials. While some permanently shadowed regions contain ice, the distribution is limited and highly dependent on specific geographic conditions. The Moon's lack of atmosphere and geological activity means that resource formation processes are effectively inactive. Everything available is the result of ancient impact history and space weathering with no ongoing replenishment. Mars also benefits from a more complex interaction between surface and atmosphere. Dust gases and temperature changes contribute to slow but continuous redistribution of materials. This does not create abundant resources, but it does introduce a degree of environmental dynamism that can be leveraged in long-term planning. The Moon remains static in comparison with little to no redistribution of materials after initial formation and impact processes. From an engineering standpoint, Mars offers greater flexibility in designing resource extraction systems. Multiple resource types can be accessed within a single environment, including ice gases and minerals. On the Moon, systems must be optimized for extreme efficiency and recycling as external inputs are minimal. This difference influences not only extraction methods, but also the long-term sustainability of human presence. Biologically and operationally, resource availability directly impacts survival strategies. Mars allows for partial closure of life support loops using local materials, while the Moon requires near-complete internal recycling or external resupply. This distinction does not eliminate the difficulty of living on Mars, but it changes the structure of dependency in a meaningful way. At this stage of comparison, Mars emerges as a world with limited but varied resource potential, shaped by its atmosphere, subsurface ice, and geological history. The Moon remains a far more restricted environment, where resources are sparse, localized, and largely static. Both environments require advanced technological systems for utilization, but Mars offers a broader foundation for sustained resource development. Communication between Earth, the Moon, and Mars is governed by the fundamental limitation of signal travel time across space. Electromagnetic signals, including radio and laser communication, move at the speed of light, which is finite and constant. This means that distance directly determines how quickly information can be exchanged. In the context of human operations beyond Earth, this delay becomes a critical factor in coordination, safety, and decision-making. Between Earth and the Moon, communication delay is extremely short. Signals travel quickly across the relatively small distance, separating the two bodies, resulting in near real-time interaction. This allows for direct operational control, rapid feedback, and immediate response in many scenarios. Human systems on the Moon can maintain close synchronization with Earth-based teams, enabling centralized decision structures and continuous monitoring without significant delay in most cases. Mars exists in a fundamentally different communication regime. The distance between Earth and Mars varies depending on their orbital positions around the Sun. At closest approach, signals still require several minutes to travel in one direction. At greater distances, this delay can extend significantly longer. This creates a communication environment where immediate response is impossible, and all exchanges are separated by meaningful time gaps. This delay affects not only conversation but operational control. On the Moon, instructions can be adjusted in near real time, allowing for dynamic problem solving. On Mars, decisions must often be made locally, because waiting for Earth-based input would introduce delays that could compromise safety or efficiency. This leads to a shift in autonomy, where Martian systems and crews must operate with a higher degree of independence compared to lunar systems. The Moon's communication advantage also affects emergency response. In the event of a system failure or unexpected environmental hazard, Earth-based teams can rapidly analyze data and provide guidance. The short delay allows for iterative troubleshooting and continuous adjustment. On Mars, however, the delay means that by the time a message is received and a response returned, conditions may already have changed significantly. This requires pre-planned protocols and autonomous decision frameworks rather than real-time oversight. Signal degradation is another factor influenced by distance. While both environments allow for relatively clear transmission pathways due to the lack of atmospheric interference in space, Mars communications must traverse a far greater distance through interplanetary space. This increases the importance of signal strength redundancy and error correction. The Moon benefits from a simpler communication geometry with fewer delays and less signal attenuation. The psychological impact of communication delay also differs between the two environments. On the Moon, the near immediacy of contact with Earth can help maintain a sense of connection and support. On Mars, delayed communication introduces a temporal separation that can affect planning and coordination rhythms. Information exchange becomes structured in cycles rather than continuous interaction, shaping how teams operate and respond to changing conditions. Operational planning on Mars must account for this delay in every layer of system design. Navigation, resource management, and emergency procedures must be executed with local autonomy in mind. On the Moon, systems can remain more closely tied to Earth-based command structures. This difference fundamentally changes the architecture of human presence in each environment. Even scientific observation is influenced by communication timing. Data collected on the Moon can be transmitted and analyzed rapidly on Earth, enabling near-continuous feedback loops. On Mars, scientific data arrives with delay, meaning that analysis and interpretation occur in a staggered sequence. This affects how experiments are designed and how quickly conclusions can be integrated into ongoing operations. From a systems perspective, communication delay becomes not just a technical limitation, but an organizing principle. Lunar operations function within a tightly coupled Earth-Moon system, while Martian operations function as semi-independent systems within the broader solar network. This distinction shapes infrastructure decision hierarchies and even the psychological experience of distance. At this stage of comparison, the Moon represents an extension of Earth's communication environment where near real-time interaction is still possible. Mars represents a separated communication domain where distance imposes unavoidable delays that reshape autonomy and operational structure. Both environments remain connected to Earth, but the nature of that connection differs fundamentally in timing control and dependency. Infrastructure on the Moon and Mars develops under entirely different external constraints, even though both environments require sealed habitats, life support systems, and protection from space conditions. The process of building stable structures in either location depends on how materials behave under local gravity, how the surface interacts with engineering systems, and how long-term exposure to radiation temperature change and mechanical stress accumulates over time. These factors define the difficulty of establishing durable human presence beyond Earth. On the Moon, construction begins in an environment of vacuum extreme temperature variation and high radiation exposure. There is no atmosphere to protect exposed structures during assembly, meaning that every stage of construction must account for direct interaction with space. Materials must be transported positioned and joined in conditions where outgassing, thermal expansion, and radiation effects occur simultaneously. This creates a highly controlled engineering environment where small errors can have immediate consequences. Lunar gravity is low, which reduces the structural load on buildings. This allows for lighter frameworks and reduces stress on foundational supports. However, this advantage is counterbalanced by the absence of atmospheric pressure, which means that all internal spaces must maintain full structural integrity against a near-zero external environment. The pressure difference between inside and outside becomes one of the dominant design challenges. Any failure in sealing can result in immediate loss of internal atmosphere. Mars presents a different set of construction conditions. Its thin atmosphere provides some environmental buffering, meaning that structures not directly exposed to vacuum. This allows for more flexible construction techniques compared to the Moon. However, Mars introduces its own challenges through atmospheric dust, seasonal pressure changes, and temperature variation. These factors require materials that can withstand both mechanical abrasion and chemical interaction over time. Martian gravity is stronger than lunar gravity, which increases structural load requirements. Buildings must be designed to support greater weight-making construction, more similar to Earth-based engineering in terms of gravitational stress. However, this advantage in familiarity is offset by the need to operate in a cold, low-pressure environment with limited oxygen and frequent dust activity. Structural systems must therefore balance Earth-like gravitational demands with non-Earth atmospheric conditions. Thermal stability is another major factor influencing infrastructure design. On the Moon, structures must withstand rapid and extreme temperature changes between prolonged daylight and darkness. This requires insulation systems capable of handling sharp thermal gradients without material fatigue. On Mars, temperature changes are more gradual due to atmospheric moderation, but still cold enough to require robust thermal protection. The difference lies in the rate of change rather than the absolute severity of cold conditions. Radiation exposure also affects infrastructure longevity. On the Moon, structures are directly exposed to space radiation unless heavily shielded. This necessitates the use of regolith-based covering or subsurface construction to reduce exposure levels. On Mars, the atmosphere provides partial shielding, slightly reducing radiation impact on surface structures. However, long-term habitation still requires additional protection, especially for sensitive equipment and biological systems. Dust interaction plays a significant role in Martian infrastructure maintenance. Fine particles carried by wind can accumulate on surfaces, infiltrate mechanical systems, and reduce the efficiency of energy collection systems such as solar panels. This requires continuous maintenance strategies or protective design features. The Moon lacks atmospheric dust transport, but its regolith is mechanically abrasive and can still contaminate equipment through direct contact. Subsurface construction is a key strategy in both environments. On the Moon, underground habitats provide protection from radiation temperature extremes and micrometeorite impacts. Excavation or use of natural formations becomes essential for long-term stability. On Mars, subsurface environments offer similar benefits with the additional advantage of potential ice deposits that can contribute to environmental control and resource access. This makes underground or partially buried structures particularly valuable in both settings. Energy systems also influence infrastructure design. On the Moon, long periods of darkness require energy storage systems capable of sustaining operations through extended night cycles. On Mars, energy production is more continuous but disrupted by dust storms and seasonal variation. This difference affects how infrastructure is integrated with power systems, including redundancy and distribution networks. From a systems perspective, lunar infrastructure tends toward compact, highly controlled and heavily shielded designs due to extreme external conditions. Martian infrastructure can be more distributed and flexible, but must account for environmental variability over time. Both require advanced engineering, but the balance between rigidity and adaptability differs significantly. At this stage of comparison, the Moon represents an environment where infrastructure must be engineered for absolute external hostility, requiring maximum isolation and protection. Mars represents an environment where infrastructure must adapt to a broader range of changing conditions while still maintaining protection from a harsh but less extreme external environment. Both remain far from naturally supportive, but the nature of structural challenge differs between rigid isolation and adaptive resilience. Long-term survival on the Moon and Mars depends on how all environmental factors combine into a single sustained pressure on human biology, engineering systems, and resource cycles. At this deepest level of comparison, no single condition determines habitability alone. Instead, radiation exposure, temperature, instability, gravity differences, communication delay, and resource availability interact continuously, shaping the overall risk profile of each world in different ways. On the Moon, survival is constrained by an environment that remains extremely close to the conditions of space itself. The absence of atmosphere means that radiation, vacuum exposure, and temperature extremes are constant background forces. There is no natural buffering system that reduces variability over time. Every external factor is direct, immediate, and unmoderated. This creates a situation where stability must be entirely manufactured through engineering with no assistance from environmental processes. Mars, while still hostile, introduces a thin atmospheric layer and more complex environmental cycles. This does not make the planet safe, but it changes the structure of risk. Instead of constant direct exposure, conditions vary with seasons, dust activity, and atmospheric density. Radiation is partially reduced but still significant. Temperature changes are less abrupt but still extreme compared to Earth. Resource access is broader but still limited. This creates a layered environment where challenges fluctuate rather than remain constant. The human body responds differently to these two environments. On the Moon, physiological stress accumulates rapidly due to low gravity, high radiation, and isolation from natural environmental cycles. Bone density loss, muscle degradation, and radiation exposure progress under relatively uniform external conditions. On Mars, the same biological stresses exist, but the presence of slightly stronger gravity and partial atmospheric moderation alters their rate and distribution. The body still cannot adapt naturally in either environment, but the trajectory of strain differs. Engineering systems also face contrasting survival pressures. Lunar systems must prioritize absolute containment. Every habitat, suit, and machine operates against a near-perfect vacuum and extreme thermal cycling. Failure tolerance is minimal because any breach immediately exposes internal systems to space conditions. Mars allows for slightly more environmental interaction, but introduces its own maintenance burden through dust, atmospheric chemistry, and seasonal variation. Systems must be more adaptive, even if slightly less isolated. Resource sustainability further separates the two environments. The Moon requires near-total dependence on internal recycling and external supply chains, with only limited local resources such as polar ice and regolith-bound oxygen. Mars offers more diverse local materials, including water ice and atmospheric carbon dioxide, enabling partial in-situ resource utilization. This does not eliminate dependence on Earth, but it reduces absolute reliance compared to the lunar surface. Communication delay reinforces this contrast in operational structure. The Moon remains closely integrated with Earth, allowing near real-time coordination. Mars operates under delayed communication cycles that force local autonomy. This shifts decision-making responsibility outward, increasing independence, but also increasing risk during unexpected events. Over time, this changes not only operations but the psychological structure of human presence. When all factors are combined, the Moon presents a more immediate and uniformly extreme environment. Every hazard is consistently present, and every system must continuously counteract space conditions without environmental support. Mars presents a more variable environment where hazards are still severe, but distributed across changing atmospheric, seasonal, and geological conditions. The Moon is defined by constancy of exposure. Mars is defined by variability within harsh limits. In long-term survival terms, the Moon imposes a tighter engineering constraint space, where success depends on perfect containment and sustained system reliability under unchanging extremes. Mars allows a broader range of strategies, but introduces more environmental variability that must be managed over time. Neither environment supports natural human survival, but the structure of difficulty differs between absolute external hostility and fluctuating planetary adversity. At the deepest level, the comparison resolves into two different kinds of danger. The Moon is dangerous because it offers almost no transition between safety and exposure, making survival entirely dependent on artificial systems at every moment. Mars is dangerous because it offers partial environmental support that is still insufficient, creating a persistent balance between assistance and threat that shifts over time. This distinction defines why living on the Moon can be considered more dangerous than Mars in certain respects. The Moon removes almost every environmental buffer, leaving only engineered protection between human life and space. Mars retains minimal atmospheric and geological systems that slightly reduce exposure intensity, even though it remains fundamentally hostile. Both worlds demand continuous technological support, but the nature of a risk differs between absolute exposure and moderated instability. End of script. Sleep well,